Okay, greetings, friends. Here we are in the last class for week 11, and that means we've got PLC for Friday of this week, which for me is tomorrow, and Homework 5 Celebration 2 is happening on Thursday of next week. So today we'll go through and probably put the finishing touches on the thermo stuff that we wanted to talk about, and we will move into modern physics starting next week. So we'll have weeks 12, 13, 14, 15. Oh, that's not bad. So we'll have 4 weeks on modern physics, which is great. We'll concentrate on getting going on special relativity starting next week. So in terms of celebration, same mechanics as last time. There will be no class on Thursday. There will be celebration open all day. Pick your time. Know your time amount, right? We're going to start at the same 2-hour nominally, and then anything extra goes on top of that. So know how much time you have. Get it sat down and fixed up, and off we go. Alrighty. In terms of coverage, it's all thermo. I'm not putting any optics from the first section on there. So we're starting with the laws of thermo, which we began right after finishing the optics. And we've gone through first law stuff, ideal gas, second law, and what we're going to get done today, a little bit of extra stuff and some heat transfer, and we will call that good. Alrighty, so final, in terms of final, we're going to be looking at coverage from everything, and typically what I do is I divide half and half. So beginning next week, we'll start material that will be on the final in about the ratio of about 1/2 approximately, and then from celebrations 1 and 2 material, I'm going to take that other half of the final and I'm going to use that material. So it's going to be a kind of a two-pronged situation here.
Is the final going to be on the 27th, like it says in the syllabus?
I think that date is not correct. I must have missed it by a week, so it should probably be the 20th.
Thank you. And do you know what time it's scheduled for, or is it
It's going to be the same as the other ones. It'll just be open for whenever you've
okay.
got time during the day.
Awesome. Thank you.
Mm-hmm. We're going to start off today and spend some time talking about statistical behavior. This is a topic which I haven't assigned any homework problems on, but I want to introduce as a way of thinking, just like we had the Maxwell speed distribution, and we thought about, well, what does it look like when, or how can we use that when molecules are evaporating from a liquid, or when things are condensing, even when the temperatures are not actually at the phase change temperatures. Okay, so the things we measure, like pressure, temperature, and assuming we have an ideal gas, we've kind of talked a little bit about this. These macroscopic things we measure are results of basically system averages, in the sense that we have so many particles of an ideal gas. I'm in a room, and if you look around the size of the room you're in, you could try to estimate how many particles of gas there are in the room. It's going to be kind of a lot, you know, like more than you can count on your hands. So the behavior that we end up measuring is a statistical average of the behavior of all of these particles. Now, that's not to say, and we addressed this a little bit when we were talking about the mechanical model of the ideal gas, that's not to say everything has that behavior, right? When we talked about the speeds of the molecules, it's unlikely that many of them have the actual RMS speed. Many of them will have the most probable speed, but the idea is that there's a spread in these things, okay? So what we have to end up doing is thinking about an average. What I'd like to do is introduce a way of thinking about this, which was first introduced by Boltzmann, and he delved into how do we get to a system average when we have a system with so many interacting particles, so many pieces to it, okay? Like I said, the numbers are huge, okay? So you can start off with the number of particles that comprise a mole, right, which is 10 to the 23rd of them, and you can go from, we're going to be going up from there. So that right away is a huge number. So there's no way we can keep track of everyone's behavior. Let's try to keep track of a statistical average. So let's start off by looking at a system in which only two outcomes are possible. Okay, so this is the for example, the penny. We're flipping a penny, and it's going to end up heads or tails. You could certainly extend from that. For example, this classroom here, I'm looking at here. I could ask, if I put a divider right down the middle, I could imagine that there's a gas particle either on the left side or on the right side, okay? Just like that would be basically akin to having a heads or tails outcome. It's either this way or it's this way, right? So let's take a look at a system where I've got just a couple of components to it, and they have only the outcomes of, for example, I take two pennies, they have only the outcomes of one or the other, heads or tails. So let's start here with two pennies. And the outcomes, when I flip them, are heads or tails, and I'm going to denote these with arrows. Let's suppose that if it's heads, it's landing upwards, and tails, it's landing downwards. Okay, whatever you like. I'd like to do that because it's a lot easier to diagram the possible outcomes. Okay, so if I have just the one penny and I'm flipping it, I can either end up with the penny heads, penny tails. If I have two and I'm flipping them at the same time, and then I'm going to look at the outcome of the two pennies getting flipped. What is the outcome, or what are the possible outcomes from random flipping? Okay, and hopefully you'll notice that when I'm saying random, right, I'm taking the two pennies and I'm flipping them up like this and catching them, and I'm going to do this several times maybe. But the idea is that that's like the motion of gas molecules. It is random, right? They're going around doing this, doing that. So their behavior, and this is the great part about statistics, their behavior, even if it's random, can actually be quantified. This is a large portion of statistics, which is just dealing with randomness. And so Boltzmann took this idea and he applied it to nature's systems in which there are large numbers of particles. Possible outcomes from the two penny system, very straightforward. I think we can have, and by the way, I can distinguish between the pennies, right? I've got the one that's slightly more brown than this one, or this one's slightly more coppery looking than that one, whatever it is. I can distinguish between them. I can say that they both land heads. I could say they both land tails. And then I could say that one is one way or one is the other way. Right, that's basically our four possible outcomes. Okay. I want to put some language behind these things. Okay. So each one of these, I'm going to call it a microstate. Okay, so in other words, having two heads is a microstate. Two tails is a different microstate. Each one's called a microstate. Therefore, I have a total of 4 possible microstates. Now, when I think about all of the possible microstates, I'm going to kind of classify them, okay? I'm going to classify them. First thing I want to do is say, all right, I've got the possibility of both landing in heads. How many different ways can I have that? Well, one, right? There's only one way in which I can have both pennies landing heads up. Notice that that's different if I ask the question, what's the way in which I can have one heads and one tails? Well, I have 2 possibilities for that, okay? I have 2 possibilities for that. So what you'd expect if you did this a large number of times, okay, just thinking about generalizing this behavior to if I flipped these 2 pennies, 1,000 times, what do you expect would happen? Well, it's more likely that I'm going to end up getting one of these states, right? One of these microstates. It's more likely because there's there's double the possibilities than getting one of these, because there's only one way I can have all heads or all tails, but there's 2 ways that I could have one heads, one tail. Therefore, what you might expect if we idealized this is that if I flip these pennies a large number of times, that the more likely outcome is one heads, one tails. And if you thought about what number would you assign to that, looks like it might be about half, right? Half the time it should come up with one of these, a quarter of the time it should come up with one of those, and a quarter of the time it should come up with one of those, right? I mean, these are the only possibilities we're working with. Since these are basically the same outcome, kind of, right? I know I can distinguish them, but it's a situation of one heads, one tails. This is called a configuration. And so if we put this into this type of verbiage, we would say there's 2 microstates in this configuration. There's only one microstate in this configuration, all heads, one microstate in the all tails configuration, but there are 2 microstates in the one heads, one tails configuration. Okay. Let's look at 3 pennies. Okay, let's look at 3 pennies. I want to just go one more. If we look at 3 pennies, what are the possible outcomes? And then from this, we're going to make some generalizations. Okay. If we look at 3 pennies, I'm going to start doing the same thing with the arrows. So we've got arrows that could be all heads or all tails, right? So those are their singular microstates in each of those configurations. There's only one way of this, and there's only one way of that. Okay, so if I think of, for example, let's do 2 heads and 1 tail. Okay, so if I do 2 heads and 1 tail, I can get 2 heads and 1 tail, or I could get, actually I want to do this over here. I'm going to do this over here so I can, no, we'll do that. This is fine. I'm going to just get down here. All right, so I got 2 heads, 1 tail. So if I do that, I'm going to get this, or this. Right? I gotta have 2 upwards arrows. Right? So I've got those possibilities. That's 2 heads, 1 tail. If I go to 2 tails, 1 head, then I'm going to do basically the same type of thing. 2 tails, 1 head, like that, and I'm just going to cycle that through here. And now we've got that, like so. Let's see, if I have 2 tails two tails, one head. So I've got one, and here I've got one. Okay, good. I think that's it, right? I think that should be it. So here in this case, if I look at the configuration of two heads, one tail, there's three ways of having that. If I look at the configuration of two tails, one head, there's three microstates, three ways of having that. Configuration of all heads, one microstate. Configuration of all tails, one microstate. All right. I want to start drawing some conclusions here, or actually maybe generalizations and then some conclusions. As we go higher in penny number, okay, it looks like the configurations of all heads and the configuration of all tails stays at one microstate each. So if I go to 10 pennies, there's only one microstate with all heads. There's one microstate with all tails. However, as I go to 10 pennies, two heads, one tail, two tails, one head, and then you go to 5 heads, 5 tails, 4 this, 6 that, blah, 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 right? Those microstates, or I should say those configurations, have many more microstates than these configurations, okay? So as I go to larger and larger numbers, there's only ever one of these microstates in this configuration. That ultimately makes it less and less and less likely, if you follow, yeah? Because the way we're thinking about this is, what is the probability of getting a particular configuration? Well, does it make sense that the probability is the number of microstates that you have in that configuration divided by all the possible numbers of microstates? This is a kind of a working definition of probability of, let's get the probability of a configuration. Kind of like what I said here in the 2 penny case. What's the probability of this configuration? One heads, one tail. Well, it looks like I'm going to get that twice as much as I'm going to get one of those or one of those. Okay? Therefore, this is going to roll in at about half, and each one of these is going to roll in at about 1/4. Therefore, the probability of a configuration is equals, well, let's go equals the number of microstates in that configuration divided by the total number of microstates. Let's put that equals something down a little bit further. Okay, we could call this the probability, call it like capital P or something like that. The probability of a particular configuration is the number of microstates in that configuration divided by the total. So in this case, this is 2 divided by 4, and so half seems to be a good number. The probability of this, 1 divided by 4, 1 divided by 4. In this situation, I'm going to get 3 if I want 2 heads, 1 tail. I'm going to get 3, and it looks like I've got 8 total. But this is now down to 1 in 8, and that's also down in 1 in 8. And as I go to 5 pennies and 10 pennies and 100 pennies, this never changes. There's only ever one microstate in that configuration of all heads. But the total number of microstates, can you see, gets really large. Therefore, the probability of getting this to happen is really getting smaller and smaller as you increase the number of pennies. Okay? So take this and make a bigger case out of it. Instead of 3 and 5 pennies, 5 pennies, 10 pennies, 100 pennies, What if we're talking about 10 to the 24th pennies? Now what's the probability? It's getting vanishingly small, right? So take this and generalize. Go back to the idea of put a divider down the middle of your room, the room that you're in right now. Imagine there's a divider down the middle. What is the probability of all the gas molecules in your room going on that side? Right? Each molecule has a choice. It could be over there or it could be over there. What's the probability that all of them go over there? Okay, well, what's the number of microstates? Well, 1, because that's the only time in which they're all that side. Okay, divided by the total number of microstates. Now you have to be real careful. Now we have to think of how many air molecules are there in the room. I'm going to put a little tiny flag on each one of them with a number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so here is a air distributed evenly in the room is a microstate. But what if I take molecule number 1,410,622, which is over on this side of the room, and I swap it with molecule number 8,522,616? That's a different microstate because I just swapped those two. Right? The one that was over here is now over here, and the one that was over here is now over here. I've changed their kind of heads or tails, right? That's a different microstate. So consider that even just taking molecules like that and turning like this, that's a totally different situation now, right? That's a different microstate in the configuration of molecules spread evenly in the room. Therefore, I'm hoping that you're seeing from this example that it is overwhelmingly unlikely that all the molecules will end up on one side of the room and you will suffocate if you're standing on this side of the room. And this is what Boltzmann's leap, this is his discovery, is that statistically, the behavior that we measure is a result of an overwhelming average of one particular configuration compared to all the others. In other words, the one in which things are spread evenly is it ends up being the most likely outcome, just based on the probabilities, right? And based on the number that we're dealing with. The number being so large makes it overwhelmingly likely that the average behavior is the one in which everything is spread evenly. Because these states are not spread evenly, right? These are all one way, but they have become increasingly unlikely to have happened. Now, does that mean their probability is 0? No, it doesn't. It just means it's incredibly unlikely that all the air in the room will ever end up on that side. And it turns out that you can, in fact, calculate how unlikely that is. When will this occur? You can put a number to this. If you're the type who likes doing that type of thing, which I have to admit, it's a fun thing to do. These are the questions that the burning questions we need answered. If you calculate the probability of all the air ending up on one side of the room, there are many variations of a question like this. You may have heard of another one. For example, if you take a million monkeys and put them in front of computers, keyboards, or typewriters, back when I was doing this, what is the likelihood that one of them just banging randomly on the keyboard will type out a famous literary work, something like Hamlet, right? Just banging away randomly. And all of a sudden, boop, here's Hamlet. It's spit out Hamlet just from randomly hitting the key, right? And I've got a million monkeys all doing this. What's the probability of this? Because it's not 0, right? That's one microstate in a configuration. Every other one is pretty random. So even if you get one letter out of place and you had the whole thing all perfect, you get to the very last period and instead you hit a comma. That's it. Nope, that's not it. So there's only one way of typing Hamlet perfectly, right? And there's lots and lots of other ways of typing it imperfectly. Right? If you assume one keystroke per second, how long would it take for you to wait in order for one of these monkeys to pump out Hamlet? And of course, it's way more than the age of the universe. Okay, so this gives a working definition to the idea of impossible. It's just not. Is it zero? No. Is it going to happen in reality? No. Okay, we know that that's not going to happen. All the air is not going to suddenly end up over there and we're all going to suffocate. But it could. It just is going to take a really long time to wait. I want to go through a little bit of this and think about what this means, okay, and put a little of thermodynamics behind this, because this seems to be kind of a solid left turn here. We were talking about entropy yesterday, and we were talking about PV diagrams. How is this related? Okay, hold on. Give me a second here. Give me about a half hour, really. If you go through and you look at the possibilities here, putting a few numbers behind this, you'll notice something, and that is that the total number of microstates is related to the number 2, because we only had heads or tails, to the number of pennies that I was dealing with. So starting with 2 pennies, the total number of microstates possible is 2 to the n. That would be 4. Right? So we can calculate the total number of microstates as 2 to the capital N, where N is the total number of pennies that I'm dealing with, or gas molecules, if you'd prefer. And the 2 comes about because we're considering heads or tails and nothing else. So there's only 2 possible outcomes. And that's why I decided divide the room in half. The molecule's either over there or it's over there. 2 possible outcomes, okay? So 2 to the capital N is the total number of microstates, right? And then the number of microstates in a configuration, right? We can go over here and take a quick look at that. The number of microstates in each configuration. We can actually count those. Right? It's actually pretty interesting because if you look at the distribution here, and you probably noticed it here too, if I put numbers here, this would be one of those, and then kind of 2 of those. If we look at this one, it's one of these, 3 of these, and 3 of these. Wouldn't it be kind of interesting if I could just do something like mathematically express these arrows in an equation form? Would it be possible to write all of the possible outcomes by doing that? Right? If I FOIL out this thing, I'm going to get, right, that times that. That times that, and then I'm going to get one of those there and one of those there. So this is actually related to what's called the Pascal triangle, right? Where I don't know if you know the Pascal triangle, but the Pascal triangle gives you all of the binomial coefficients that would go in here, and you can get it just by doing putting ones here and then adding, right? When I get to this here, when I get to the middle one here, I just add it, all the ones that are in the middle. So there's always a 1 on the side. Now I've got 2, 1, 2, 1, and 1, right? And lo and behold, 1, 2, 1 is that. 1, 3, 3, 1 is this. Yeah, that's not a coincidence, it turns out. Okay, so what we can do is use the Pascal triangle in order to count the number of microstates in each configuration. Okay, the number of microstates in each configuration, which is the numerator here in the probability, number of microstates in each configuration. You may, if you have a textbook that you like to look at, they will often call this W. The number of microstates in each configuration. It's also known as capital omega in the Greek alphabet here. And what we do is we can say that if I wanted to find out what the total number of microstates in each configuration was, it's just the mathematical expression for how I get these binomial coefficients. So what you do for that is you use factorials. Right? So you'd say, well, I'm going to take my 3 pennies or my 2 pennies factorial divided by having them come out one way, having them come out the other way. So that if I was interested in thinking of the number of like the number of heads, right? So if say N1 was the number of heads, I want to count how many states there are for say 2 heads coming out when I've got two pennies. If I got 2 pennies and 2 heads, how many microstates do I have in that configuration? Okay, so if I did 2 pennies and they came out to be both heads, then what I would do is I would go 2 factorial on the top for the capital, because I got 2 pennies. And then I would say, well, I want to calculate how many microstates are there in the configuration of 2 heads. So I do 2. And that means there's no tails. This is 0 factorial. And 0 factorial is 1, thankfully. Because 2 factorial over 2 factorial is 1, then 0 factorial is 1. So this turns out to be 1. If I go to the 3 penny case and I want to know how many are there in 2 tails, if I go to 3 pennies, 2 tails, then I would do 3 factorial for the pennies. I would do 1, there's 1 head, so that's 1 head, 2 tails. 3 factorial over 2 factorial, 1 factorial, well, that's just 3, because the factorial is just the multiplying, right? So 3, 2, 1, and that's 2, 1, so it turns out to be 3. Yeah, indeed, this tells you the number that comes next. Here it is, 3 factorial divided by 2 factorial, 1 factorial. So it tells you how many microstates there are in each configuration, where little n1 is the number that occur in one way, and little n2 is the number that occur in another way. Okay, so that's what these things here mean. Capital N is still the same thing as the total number of pennies, where n1 and n2, I just said call n1 the number of heads and n2 the number of tails. Okay, so this is the way that you count the total number of microstates in a given configuration. And that means that when I look at the probability, it's basically this thing here divided by 2 to the capital N. All right. Now, I don't want to get into a big math breakdown of all of this because it's not really the point of the conversation here. The point of the conversation is I've done this for 2 pennies and 3 pennies. Now imagine doing it for 10 to the 24th pennies. What's going to happen? Well, I will tell you what's going to happen. What's going to happen is that the probability is going to spike right around the very middle of having things evenly distributed. Okay? And even one off that, the probability is going to have skydived, right? It's gonna be so low compared to the probability of the 50-50 state. Okay, in other words, divider in the room, half gas on that side, half the gas molecules on that side. That's the most overwhelmingly likely situation because it has the most number of microstates, right? In that configuration, remember I swapped this one with this one, and now I got to swap that one with this one, and now I got to swap that one with this one. And if you think about how many times you have to do that, that particular configuration has the largest number of microstates. Okay? And you're dividing that by the total number, which is 2 to the capital N, where N is a number on the order of 10 to the 24. 2 to the 10 to the 24. That's a big number. Okay? So what ends up happening is the middle state becomes overwhelmingly likely. And deviations from the middle state are statistical fluctuations. All right, so the upshot of this is for N becoming very large. In other words, somewhere around, say 10 to the 24. Okay, that's a pretty good rule of thumb about how much stuff often there is. You're not going to be too far off. You might be off by a factor of 10, but so what? Now you're at 10 to the 25. Okay, big deal. It's still pretty much the same outcome. For N going very large, the most probable outcome is the one that has the most number of microstates, right, as you can see, but that ends up being the one that is evenly distributed, in which everything is even, right? Same number of heads and tails. I guess I should have done 4 pennies instead of 3, but you get the idea. The most probable outcome is that things are evenly distributed. Now, this is where Boltzmann made a large discovery. Nature tends to go to this, right? This is the statistically overwhelmingly likely outcome where things are evenly distributed, okay? That also corresponds with the idea that entropy tends towards its maximum value. So Boltzmann said, okay, what if the most overwhelmingly likely statistical state is the one in which it has the highest entropy? Because last time I was telling you in class that the idea of the second law of thermodynamics in a common sense way is that entropy does not decrease. And if you are managing to get the entropy to not decrease, you're doing something very, very carefully. However, if you just let things happen, they will go to the most likely state. That most likely state is the one in which everything is kind of evenly distributed, and that is the one with the highest entropy. So that when you look at quality of energy, the quality of the energy is all kind of right? There's nothing that's spectacularly well organized. There's nothing that's spectacularly well disorganized. It's all kind of smushed together and been statistically averaged, such that there's kind of a bland amount of energy here, and it's not really useful. Therefore, the state with the highest probability of happening is also the one with the highest entropy. And that is where Boltzmann made his, by all accounts, greatest discovery. And he decided to, well, not decided, he figured out that you can actually calculate the entropy of a particular configuration. And the way you do that is by using the Boltzmann constant. If you're not familiar with the case of B, it's the Boltzmann constant, times the natural log of the number of microstates available in the configuration, such that you can see when that's the biggest possible number, which corresponds to the largest probability of happening, right? That would be the biggest one of those numbers that we have. Because if you look at the Pascal triangle, right, the next one I would go 1, 4, 6, 4, 1, right? The biggest one happening is the one in the middle. That's always going to be the case. So the most likely outcome is the one in the middle, where this is a maximum. And when I go calculate the entropy, it's the entropy of the configuration that has the most number of microstates. And that's the one that has the highest entropy, because that's the one that's most likely to happen. And that's the way nature goes. And well, you could see probably log W or something, but that just, it feels shameful somehow to write that, because W is not, it's omega. That's the one that we want to use. That's the one. So this is actually the thing that is inscribed on his tombstone. Unfortunately, the idea that he had of the statistical distribution, or I should say the average of the statistical distribution being related to the highest entropic state and being calculable like this, was not at all received well in his time. And his time would have been around the 1880s, 1870s, right around in there, right? So just to put time into this, Carnot discovered the second law in about 1824. Clausius put the first law and second law together in about 1850. Boltzmann came along around 1870 and put the statistical behavior into the mindset of the thermodynamics. At least that's how we'd like to think of it. It was highly not well accepted at all for many years, and Boltzmann was upset about this. Very upset. In fact, he killed himself because he was upset about that. So we suffer for our science in many ways, but nonetheless, this is how when you get to large system sizes, this is how we think about it, because there's just simply no way to keep track of everything. We have to look at system behavior, and that means we're looking at the average. And the average is of huge numbers, and that means that the most probable state is overwhelmingly likely, and that's the one with the highest entropy to it. So anyways, this is stuff that's near and dear to my heart, so I thought at least take a little bit of time to talk about it, just to give you an idea of the depths that this has been thought about. And there's a whole field related to this stuff. So anyways, I'm not really going to worry too much about doing calculations with this type of thing. Like I said in the beginning, this is more of a mindset, something to think about. I don't have too much more to say about this, other than if you are going to pursue physics in the future, give this a look, because I think you might find that it's pretty amazing stuff. So we'll say that. We're going to now return to something a little bit more on the practical side. And we're going to think about how heat goes from one place to another. Now, I'm not going to, again, because I'm considering this to be our final day on thermodynamics, I'm not going to spend a large amount of time talking about this, as we are in our final day, in our final half hour or whatever we have. But I do want to at least sketch this out for you so that we have a basis of discussing heat transfer. And we will kind of need to do this a little bit when we get into the modern part anyway. So let's talk about heat transfer. How does heat go from one place to another? And ultimately, the other burning question that we have, I know we already answered the burning question about the monkeys typing Hamlet. I know that was already a burning question for you. But here's the other burning question that you probably have been on the edge of your seat to ask. If you were ejected into outer space from your space vehicle with no spacesuit, and you were, say, in the shadow of the spaceship so that you were not getting completely cooked by the sun's radiation. If you were in the shadow and you were only sitting out here in outer space, no spacesuit on, wouldn't you just freeze to death? Bam, you'd be frozen. Or would you become an ice cube like right away because space is so cold? We're going to calculate that. Let's see about approximately how long would it take so that we can get a good sense when this happens, what should you expect? Okay, so this is what we're going to do. We're going to look at heat transfer. So down, thinking about how materials transfer heat is one thing. How heat goes from one place to another. Now, it can be carried by a physical object. In other words, if I take if I take my pen here and I put a flame on this side of it right under here, eventually, well, ignore the fact that this cap is plastic in it, right? If I have a flame on this side, eventually this side's going to get hot, and the heat has gone down from this side to that side. Okay, it has gone all the way across here. How it has been carried by the material itself from here to there. How has it gotten there? It has gotten there by what's called conduction. And conduction is essentially direct contact with something. Okay? In other words, this part of the pen is in direct contact with that part of the pen. They are touching, and therefore heat can go from this to that, and it can go with that to that to that to that to that to that to that, and it can conduct all the way down, right? You are constantly in contact with air, although you won't be soon, because we're going to be talking about what happens when you get ejected into outer space. However, while you are here on Earth, you are constantly in contact with air. Air can conduct heat away from you, right? Because it is touching. So conduction is generally done when there is direct contact between two objects. And the two objects don't even have to be separate objects. They could just be different pieces of the same object. I could just slice this thing, right? And say, well, that piece is touching this piece, right? So direct contact of two things, or of one thing all the way. All right, it can go by convection. So this is a wonderful thing for birds around here. Yeah, there's some, you can see this happening, especially when there are bodies of water, like there might be a seasonal lake or a pond or something like that. Typically what you'll see is a bird kind of corkscrewing around the pond, but going up, right? Not flapping, just like soaring, but going around like this in order to catch the warmer air that is above the pond as it goes up like this. That's convection. In other words, the idea that warm air rises. This is essentially a way of transferring heat by large motion of a fluid. It doesn't just have to be gas. Certainly liquids will do the same thing whenever you have a hot pot of water, right? If you're boiling water and you have the burner underneath it, you may or may not have seen, but the water will, right? It will heat right here, but then it will become less dense, so which means it goes up here, and that means it gets replaced by the more dense, cooler water, which then heats up and it goes up here, right? So it actually sets up a stirring cycle all by itself. You don't have to do anything. So the convection is bulk. In other words, large amounts. Bulk fluid movement due to density changes. And the last one, there are only three that we're going to discuss here because ultimately this is kind of it. The idea that radiation, heat radiation. Okay, so this is the same idea so here's an example. Convection, you would have, if you lit the candle and you put your hand on top of it, it would feel extremely hot because that's the hot air going straight up from the side of the candle. But if you put your hand to the side of the candle, it will not feel anywhere near as warm as if it were on the top of it, but you will feel the warmth of the candle. The hot air generally is rising, so if you're on the side, you're missing most of the hot air rising. So you're going to miss most of the convection from that, and it will be from the side, it'll be due a little bit to conduction, which because maybe some of the air didn't expand and move up, so it may be transferred a little bit straight out, but also it will be due to radiation. In other words, the energy carried by the electromagnetic waves that are emitted when something is hot. Typically, when we talk about heat radiation, we're talking about infrared. Electromagnetic. What did I just say? It was really good. It's the electromagnetic waves carrying energy. Okay, typically for things that are in our normal temperature range, this will be in the infrared. Typically it's in the IR. We radiate a lot of infrared. The Earth radiates infrared. The sun also radiates infrared, but it's way hotter than Earth, so it actually glows white hot. When you look at flames, okay, usually you can deduce how hot the flame is from the color of it. That's not always the case because of salts and things like that, but sometimes you can change the color of it. But if it's generally, if you're thinking about a hotter and hotter flame, those are the blue ones. And if you're thinking about a less hot flame, those are the ones that are orangish, reds, okay? And then the ones in between are like yellowies. Which means that, of course, if you look at your bathroom sink taps, they got the colors wrong. The blue is cold because it's supposed to remind you of ice. Red is the hot, it's supposed to remind you of a hot fire or something, right? Well, of course, blue is actually much hotter than red, so take that for what it's worth. Whenever anything it has a temperature, anything that has a temperature, and I'm talking about a Kelvin scale temperature. In other words, any temperature above 0 on the Kelvin scale will radiate heat. Okay, everything above 0. And so, guess what? That means everything. Okay, I just wrote typically here because that's like a Newtonian. It's not Newtonian. It's like the application of Newton's laws to us, because Newton's laws work because we're big and heavy and massive, and we push stuff, and F equals ma and all that great stuff. So typically for us, infrared is the usual heat radiation. But as you know, fire is hotter than normal, and the sun is much hotter than normal. Stars are very hotter than normal, right? So this is not a rule by any means. It's just typical, like, we emit infrared radiation. Okay, so these are the 3 ways that heat transfers. What I'd like to do is take a look at the radiation first, because the other ones are fairly straightforward. Maybe if we have a little bit of time, we'll talk about some convection too, because the lab last week was related a little bit to not necessarily convection, but in a sense it is, because Newton's law of cooling is related to the convection here. What I want to talk about here is the radiation. So we have a model for radiation. We have a model for radiation emitted by a hot object, and it's known as black body radiation. Now, black body radiation, what is the meaning of this? Okay, let's talk about the model of a black body. A black body is one in which it absorbs everything that is incident upon it. Okay, it's a model. So it's not reflecting anything. So technically you can't see it, right? Visually, you can't. So when you shine light onto it, it would absorb it. You can kind of think of a black hole, right? Would be a great black body. The funny thing about this, though, is that when things are good absorbers of radiation, they are also good emitters of radiation. Okay. Therefore, in a strange circumstance, the model of black body radiation is extremely good at describing the sun's radiation, because the sun is effectively a good black body. Okay, so it doesn't literally mean the thing is black. It means that it absorbs radiation and emits radiation in a particular way. Okay. So the model can be used for lots of things. Typically, we would use it for most things that are not mirror-like, right? Because mirrors reflect just they're not absorbing. Black body radiation is the model, and it absorbs and emits radiation. It does so. It does the absorbing, but it does the emission based on its temperature. And this, I think, is sensible, because when you think about the colors of things, like I was just saying, if I have a reddish orange fire and then there's a white fire or something, or maybe there's a blue fire, I'm going to know that that's a lot hotter than this one. So in some sense, we already have this built in somehow, that the emission of radiation, the light that we're seeing, right? And this happens with light bulbs too. If you have one of those dimmer switches and you can make the light kind of go, the light color changes as you go up and down. So if you have an old style Edison bulb, the LEDs, no, it's a little different with those. They work by a different principle, not really this way. But if you look at an Edison bulb with a filament in it and you shine it full blast, it's going to be white, which is the idea. But if you turn the voltage down, right? If you turn it down and you dim it, all of a sudden it can get down to a point where you can look directly at the filament and it will be glowing red, like a red hot poker out of a fire or something like that, right? It's emitting its radiation based on the temperature of the filament. And so that would be a great candidate for a black body model, okay? Ultimately, black body radiation can be described by a couple of quantities and a nifty little equation, which I will show you here, but not for much more of a purpose other than to give you an idea of the dependence of the radiation. Okay? And of course, also to calculate in a little while, we should be calculating what the outer space thing is. So the power, we usually talk about the power radiated. By a hot object. Depends on, so how silvery or black is it? Does it reflect a whole bunch? Does it really absorb a whole bunch? Okay, so the quantity here is called the emissivity. Nope, that does not have two M's in it. There. Okay, it does have two S's. Emissivity. This pen is terrible at spelling. Emissivity. The emissivity, in other words, since emission and absorption are highly related, it's also basically how reflective is the thing, right? If you are reflecting most everything, you have an emissivity of almost 0. If you are absorbing everything, you have an emissivity of about 1. It has to do with the surface area. The surface area of the object. It has to do with the temperature of the object in, of course, Kelvin. And there's a constant thrown in there in order to make the units work out. Now, radiation is going to be the primary mode of heat transfer if you get ejected into outer space. Outer space, as you know, has no air. Convection would not be in play. Conduction also would not be in play because there is nothing touching you. You are surrounded by vacuum, and therefore the only way that you are going to be losing heat is via radiation. Okay, so here you are, you're ejected, you're floating around in outer space, and you are going to radiate your energy away. This is radiation only. We put all these together by multiplying. We say that the power, what did I say? The power radiated, that is to say the amount of energy per time, is equal to, I'll just call this, say, PR, and that's going to be equal to the emissivity times the constant times the area times the temperature, and the temperature goes to the 4th. If you can believe that, this is one of the only quartic relations that we have here in physics. This thing here is a constant. As I told you before, it's known as the Stefan-Boltzmann constant. And it has a value which is very easy to remember. It's 5, 6, 7, 8. It's like you're getting started. 5, 6, 7, 8. The units I said were here to work out correctly. So it's got whatever units it needs in order to make the power radiated come out in watts, which is joules per second. Okay, let's calculate, if you get ejected into outer space, let's calculate how much radiation is occurring. Like how much energy are you losing per time? Okay, so in outer space, I'm going to imagine a couple of guesses here at things. I'm gonna go ahead and assume I'm probably close to being a black body. Maybe I'm at 0.8. I'm not a perfect black body, but I mean, maybe I'm okay. So let's call it about 0.8 for that. Let's go with a surface area. That means if I, peeled off all my skin and measured about how much there was. I'm going to say maybe about, for me, maybe about 2 square meters worth. I'm going to make a few assumptions here. So let's assume the emissivity is 0.8. Let's assume my surface area is 2 square meters. Now, my radiation really is going to be due to my skin temperature, but I'm going to go ahead and assume that it's related to my internal energy, my internal temperature. And that's, that was about 37 or so, right? That's about 310. So if my internal temp, well, that's not really fair, I guess, though, is it? Because I shouldn't. Out the mouth, it will be 310, but out of my skin, maybe it'll be more like 300. Okay, let's go with about 300. Let's go with about 300 Kelvin. That's skin temperature. Right? That'll be the bulk of what I'm giving off is my skin temperature. Now, if you ever looked at yourself under an infrared camera, you'll see that your eyes, your mouth, and your ears are really hot compared to the rest of you. But let's go ahead and ignore that because most of the rest of you is going to be emitting a little bit more than room temperature. So around, it'll be about 300, say. If I calculate this, how much power am I radiating? Here I am in outer space, so how much power? It's going to be just the multiplication of all this stuff, and then the temperature goes times 300 to the 4th, which is huge, right? But I've already got a 10 to the minus 8th here. So 2 square meters. I've got 5, 6, 7, 8. And I've got 300 Kelvin, that's to the 4th, okay? So if you take a look at this, that's about 1.5, 2 times 1.6, 1.5-ish. So that's about 1.5. 300 to the 4th, well, this is the same as 3 times 10 to the 2. That's to the 4th, so that's going to be 3 squared is 81, or I should say 9 squared is 81, and times 10 to the 8th. So that 10 to the 8th is going to cancel that 10 to the 8th. So I get 81 times 5.6, 81 times 1.5. Let's see, that's going to be about 6. That's a little less than 6, so we're looking about 4 plus about 480 plus 240. I'm going to say it's about 480 plus 240. So it's about, what did I just say? 480, 240 is about 700. So say it's about 700. It's about 700 watts. Because that's not 6. I thought it kind of was. So it's less than 700. But let's say you're radiating about 700 watts. Okay? It's close. Maybe it's not exactly, but I'm just trying to do this quickly without getting the calculator. So 700 watts of radiation, that's 700 joules per second. Right? How much has my temperature dropped in, say, 30 seconds? Right? So in 30 seconds, that is, in 30 seconds, that means I've lost energy of 700 times 30, which is 21,000. I've lost about 20 kilojoules. I've lost about 20 kilojoules worth of energy, about 20,000 joules. Okay. Back to what has that done to me? Am I frozen? Well, here's what's going on. I'm assuming that Q is about 20 kilojoules. And I'm going to say that's going to be equal to M, C, and delta T. And I'm going to try and figure out what my delta T looks like. Let's assume a mass of 80 kilograms. I'm going to assume my specific heat is basically that of water, because that's what we are. We're mostly water. This is that's in kilograms, so I got to do 4,200 joules per kilogram per centigrade. And then I'm looking at what is my delta T. Let's solve for delta T. Okay. 8 times 40, that's 8 times 40 is 320, and another 0 on top of that. Wow. So this is 42,000. This is all, wow, this is way bigger, 42 kilojoules. So this is 20 kilojoules divided by 1, 2, that's 4. Wow, that's a really big number. That's like 3, is that like 300? That's like 300 and, more to say, it's around 340 kilojoules. 340,000. So this number, delta T, per centigrade, is delta T, which is around, so it looks like it's less than 0.1 centigrade. So I will have dropped 0.1 of a centigrade in 30 seconds. So I have not frozen. At least if I got that calculation at least somewhat in the ballpark, which I think I did. But, so I'm nowhere near freezing. If I'm losing a 0.1 degree in 30 seconds, that means I'm losing 1 degree every 300 seconds, and 300 seconds is about 5 minutes, and I got to go about 30. I got to do, say, 40 degrees worth of temperature losing before I get to be totally frozen. Or at least down to 0 centigrade. I'm not even frozen if I'm down at 0 centigrade. I'm long dead. But the idea is, if you're out in outer space for 30 seconds, good news, you're not frozen. And this answers the burning question that you were concerned about. So there you go. You will, of course, have other issues, like trying to hold your breath. That will be very difficult. You will also not react very well to the reduced pressure outside, because basically there's 0 pressure and we're used to getting atmospheric pressure kind of holding us together. So you will start leaking when you get out into outer space. But if you can get rescued quickly enough, then hopefully you'll be just fine. I would say you probably have a good 30 seconds to a minute before really bad things start happening. But freezing is not one of them, so you don't have that to worry about. Good. Well, I think we're just about done.
Hollywood has lied to us all these years.
All these years, all these years. But you know who doesn't lie is The Hitchhiker's Guide to the Galaxy, in which people get ejected into outer space. Ford and Arthur get ejected into outer space. They manage to hold their breath, and after 29 seconds, they are rescued. So that is that's a very good depiction. I'm happy enough with that. So there you go. Your burning questions of the day answered. Monkeys typing Hamlet, freezing in outer space. What else is there? I guess that's about what we have going on today. So good luck. Stay tuned. We'll have a interesting lab starting tomorrow for those of you doing the labs on the Fridays. We'll get you started with a pretty fun little project going. And as far as this class, I will see you back here on Tuesday of next week. I think that pretty much covers it for thermodynamics. So we will say celebration next Thursday. And good luck, study up, and I will see you then.